can let them know. All right, so thank you, perfect. So we're on page 168, and this is number 88. Awesome, let's take a look. So it says, if you stand on a bathroom scale, the spring inside the scale compresses 0.6 millimeters, and it tells you your weight is 760 newtons. Now, if you jump on the scale from a height of 1 meter, what does the scale read at its peak? So think about it first. When you jump on a scale, it's going to shoot up, right? When you land. And then when your body comes to rest, you're going to see that the actual scale will stop at oscillating between the values. So the first thing we have to do is look at this and ask ourselves, what are we given? We're given the spring inside compressing a certain distance, and we're given a force. So the spring inside of the scale compresses, I'm going to put delta y, okay, because it's vertical. It's a spring that's vertically adjusted or oriented. And it's 0.6 millimeters, which is really going to be 0.006 meters. Now the force felt by the spring or the scale tells us that your weight is 760 newtons. Okay, so that's what we've got. We've got a force and we've got a all right, so the force of the spring scale tells us that it's 760 newtons that the scale is reading as a result of this. All right, so right away, let's start by finding out our K value. So if we remember here for this chapter, Fs equals negative K delta X. I'm going to put a delta Y here, again, simply because it's a vertical spring, because it's a scale. Let's see. The delta Y, the initial height is some value. The final height is some value smaller, right? If we think about this, I'll draw a picture of it so you guys can see it. This is what the spring inside of the scale looks like normally. And then when you step on top of the scale, this is now what it looks like. Okay? It goes from being a length that has an endpoint here to an endpoint right here. So as a result, we know that the initial and the final y value or length of the spring changes. So we could say here that the delta y is the final length, which is shorter, right? Let's look at this. We've got a final length here minus the initial length. So we've got a smaller number. Do you need the room? I'm sorry. I'm only using it because they took my room next door for the foreign languages. Okay? I just saw Chris in there. That's why I didn't go in mine. Okay. Sorry. So the final length, again, is going to be shorter than the initial length, and we're doing final minus initial. So really what I'm getting at is the fact that this quantity, 0.006, is really negative also. So this compression is actually a negative value. And again, I'm thinking about it, like think about this as being 1 millimeter, right? And then it goes down to 0.4 millimeters, millimeter. And that's what the scenario is. You get on the scale, it compresses it. So final minus initial is going to be 0.4 minus 1, which will give us really a compression of negative 0.6 millimeters. So we have our formula here. We'll throw 760 in place here. The K value is unknown. The delta Y is negative 0.0006 meters. So we'll solve for K. Why did I just make a big fuss about the negative signs? Yeah.
Don't you cancel out?
Yeah, K's got to be positive. K is a positive quantity always. So you had to have a double negative somewhere there, right? So I know that the spring force, which way is the spring pushing if you stand on a scale? Which way does the spring push? The spring is being compressed, so which way does it push? It pushes back up. So I know that the spring force over here has to be a positive. So that reminded me that my delta Y is going to be a negative quantity. Remember, these are always opposite signs. Write yourself a note if you didn't remember that. These are always going to have opposing signs on them. Okay, the spring force and the delta Y. So K will turn out to be I need your help with this. I don't have a calculator. 760 over 0.006. It's going to be a very large number. 1,266,600. Newtons per meter? Good? Okay. And validate, please. Yeah, with each other, please. So that's the K value of the scale. why am I going through all of this effort to find the K value of the scale? We haven't even gotten to the problem yet, right? But I jumped into find the K value. What do you think? What's the reasoning for why I'm looking for the K value? Go ahead, Jen.
Oh, it's a constant. So
K is a constant, good.
you want to change. So when you're using the spring from a different height, I think, the number's the same.
Good. When we're going to jump on this scale now, right? It says next, you jump on the scale from a height of 1 meter. Figure out what the scale reads at its peak. So, if we want to read what the scale reads, the scale's reading is right here. Take a look at what I'm circling. That's the scale's reading. And I know K now, don't I? So if I could figure out what the compression is as a result of me jumping on this, the maximum compression, I can plug in that number right here, multiply it by K, and see what the scale reading is. So the question is, am I going to be able to compress the spring all the way? If I can compress the spring all the way, well then I would have a certain value that I would use here, and I would plug that value in and then solve for this. So let's go ahead and do that here. So anyway, let's go into look at the problem now. So here's you, right? You're jumping from a height of 1 meter. So we've got this value here as 1 meter. Here's the scale, and the scale has a spring inside of it, and then there's a surface on the bottom of the scale. So when you land on that scale, right, as you fall in this direction, you start falling, falling, falling from a height of 1 meter, and you hit the scale, this spring right here is going to get compressed. All right, that spring will get compressed, and we can figure out how much is compressed using energy, using our conservation of energy. So if we are jumping, it says from a height of 1 meter. We're not given a velocity with which we jump, so we have to assume that you're literally doing this. You're here, right, and you're just going. That's the jump you're making. So what am I getting at by doing that kind of a jump? What would V1 be, or the velocity be when I'm jumping? What would we have to assume it is?
0.
You have to assume it's 0, because we're not given any information about you jump on the scale with a velocity of this. You can't figure that out. There's no way to determine it. So what we would say here is that you have only gravitational potential energy at the beginning of this problem. Okay, because you're like falling from a height of 1 meter. You then hit the scale. When you hit the scale, you'll have a little bit of gravitational energy still, and then you'll also have kinetic energy when you hit the scale. But we don't care about that kinetic energy because we're not asked about the velocity that we hit the scale with at all. So I don't need to know what the kinetic energy is. I don't have to worry. So what I want to think about is this. This is the total energy in the system in the beginning, right? UG. So that value is the total energy in the system at any moment. So when this spring is compressed as much as it is, we'll say that the energy that you have gravitationally could equal the energy you have in the scale. Okay, and what we'll do is we'll also have to recognize that we may have some gravitational energy still, because you might have still have some height. The problem we're going to run into here is that we don't know how long the scale spring is. We just know that it was compressed this distance earlier, right? But we don't know that it's actually 1 millimeter. I just wrote that number down as an example. And I said it goes from 1 millimeter to 4, which is what, or 0.4, which is what gives us this change. But we don't really know the actual length of the scale. So let's talk about how to approach this problem if we don't know that. So we're still going to call this ground level. Okay, we're going to call that ground level where we land on the scale. I cannot call where the scale ends up stopping ground level because I don't know, again, what that length of the scale is. So it's not possible to do that. So I'm just going to call the top of the scale ground level. Now, when you fall and you hit this scale, it's going to compress the spring to look like this now. Right? And the new top of the scale is going to be here. Do you all see what I'm drawing there? Yeah, I just drew in this little bit right here in the bottom right. So the scale is going to get compressed a certain distance, and that's going to be our delta y, which we can then utilize to find out the spring force. The problem we're going to run into is that we're going to have, at this moment, take a look where I'm pointing, we're going to have a negative amount of potential energy there, gravitationally. Because I'm calling this ground level, right? So now I'm technically, where am I? I'm below ground level when the scale compresses. Again, I'm here, but then when I hit the scale and the scale starts to compress, I'm now below ground level. So I have to consider that as a negative energy. So let's talk about that. We haven't seen that yet. Okay, we haven't seen the concept of using negative energy. So we've got gravitational potential energy to start the problem. At the end, we've got elastic energy for sure. And we still have some gravitational energy at the very end. Again, that's going to be a negative quantity. We'll get into how to approach that. But this is what we're looking at for sum of the energy in the beginning equals the sum of the energy at the end, right? E1 is equal to E2 in this problem. So the gravitational energy in the beginning, we've got our mass, we've got our gravitational constant G, and we've got the initial height Y1. The elastic energy is 1/2 kx squared. The next part is what's going to be tough. So this next part is still going to be mg, but then it's going to be y2. And y2 is going to be a negative quantity. Because think about where y2 is. Y2 is down here, which is below ground level. This is ground level right here. And we're interested in the problem when this scale finally comes to rest at the bottom here. That's when the scale is going to read the most. It's going to obviously spring back up, and it's going to eventually find its reading, and that number will be lower. But we want to know what the maximum the scale will read is. So we have to figure out what this value is right here. And I should really call this, instead of x, I wrote x. I should call this delta y, because we're being consistent with what we wrote earlier. So this part right over here, let me make that a delta y instead. And it's still squared, okay? Now, one of the things that we have to do, and this is not easy, but we have to figure this out, and we have to ask ourselves, well, what is our mass? Right? What's our mass? Because that's not given in the problem. But we are given something. We're given something that can help us to figure out our mass.
This is the weight is 760 newtons, and the weight is mg.
So we could just
divide 760 by mg.
Very good. By g. So we know that the weight of us in this problem, the person, is 760, because that's what the scale is reading, right? That's what we're told. We're getting this number from right here. That's the weight of the object. When I stand on the scale, my weight pushes down, and the spring force pushes back up. So that's why the spring force and the weight are the same value. They're both 760. So since weight is equal to mg, we can do this. And then as Eduardo just said, let's divide by g on both sides. 760 divided by 9.8. Go ahead. 0.6. It's okay. Good checking each other there. So that's the mass that we're going to utilize. Now, here's the other part that's a little bit, not tricky, but good to know. The delta y value that goes in for the squared term, let me point it out right here, is the same as what? Close. In the first problem it was, yes. But now we're jumping on the scale, so it's going to be different, right? We're not just standing on the scale.
1 meter.
Not 1 meter. Remember, I made this number up. That was arbitrary. I made that number up.
Would it be the same distance as y2?
It would be the same as y2. Because what's y2? Look, this is 0 height right here. And then y2 is this position right here, isn't it? So really, when we look at this, we're going to be looking at this value. y2 is however far we go down. So if I know that this height is 1 meter below where I started, then y2 is like -1 meter. That's how far I'd go down. Well, the distance that the spring compresses is going to be the same as this, except it's going to be a negative quantity here, whereas this one is a positive quantity, okay, because we're going to be squaring that in the end anyway. So when I write the next line, watch what I'm going to write. I'm going to write mgy1 equals 1/2 k delta y squared minus mg, and then I'm going to put a delta y at the end there. And I'm putting that delta y next. I'm putting that delta y there to indicate that it's the same as however far the spring is compressed. The spring being compressed a certain distance is exactly how much further you're going to go below this green line where the scale started. So it turns out that to solve this equation, what do we have to utilize? What kind of an equation is this? It's a quadratic. So you have to solve a quadratic to answer this. So I'm going to plug in numbers so we can see the numbers at this point. 77.6 times 9.8 times the initial height, which was 1 meter, equals 1/2. K is given. It's going to be a huge number. I got to figure out what it was. What was it? 1,266, 666, A lot of sixes there. Times my delta y squared. And then that's going to be minus 77.6 times 9.8 times the final delta y at the end. So that's what this equation would end up becoming. I'm trying to keep myself on the screen. My screen's different than yours. Okay. That's what the equation would end up becoming at the end that you'd have to solve to get delta y. And that's how far the spring would compress. This is kind of like the problem we did in class, but I approached it slightly differently in class. Remember the pogo stick problem? It's just like the pogo stick problem, but in that problem, we knew a little bit more about the problem. We knew about the pogo stick length, we knew about how far it could compress, we knew the length of that spring. Here we don't know enough information. We don't have the length of the spring, which is why I started using like this delta y here, right, in place of y2. And again, the rationale, and I'll zoom in so you can see it a bit better, is this. You are starting here, right? You are then, you're starting here, I'm trying to point. You are then falling toward the scale. You hit the scale right here. We're calling the top of the scale ground level. You then compress the scale by this much, stopping here. When you stop at this moment, you still have some potential energy because you're below the zero line. And that's a negative potential energy because you're below this line. And that's what yielded a negative in our equation over here towards the end. Okay, that's where this negative came into play a role when we replaced y2 with negative delta y. All right, I'm going to leave at that point, I'm going to leave this problem at that point just because, unless we have a solution already. Did you get one? Holy moly. Oh, that's your discriminant. That's not the actual solution, it's the quadratic, right? The top two are? Yeah, that's reasonable. Because think about it, right? Earlier, we compressed the scale by... earlier we compressed the scale by 0.006 meters, right? Let's compare the two. So here's what we're getting. So Francisco was nice enough to give us the value. 0.03526. I'm just going to round for now. And this is in meters. Okay, and the other answer for delta y, negative 0.034. Thank you. Now, I know I'm going to roll out the negative because I already took into account the fact that we're dropping lower, which made this symbol over here negative earlier. So the double negative wouldn't make sense there. So I know that solution is not reasonable. But this solution is. Right? This solution is. This is our delta y now. We have the delta y value, and we have the k value from earlier right here. Take your k value from earlier, multiply it by the delta y value to get the spring scale reading, because that's what this problem is actually asking us about. It says, again, determine what the scale reads at its peak, meaning at its most largest value for the scale reading. So this is the furthest that the spring scale will be compressed, which means that when it's compressed this far, the scale will read the largest value possible it can. So take the k value you got here and simply multiply it by 0.03526. So it's 1,266,666 times 0.03526. You want to give me a number for that? Just so we have it? You got it?
No, I have a question.
Yeah, ask.
Would you use negative K, though?
So, sure. And what you're going to end up getting, or what you have to end up realizing, is that this delta y as a value here, when plugged into this equation, is actually a negative quantity. When plugged into the Hooke's law equation only, it becomes a negative quantity.
So when you're graphing, I know it's not the best way to do it, but you just zoom in on the axis.
Yeah, so if you're graphing and you don't see a solution, it's probably either beyond 10 to 10, because normally you go 10 to 10, right? So it means it's bigger than 10 or bigger than negative 10, or it's super, super small so that it's practically at the origin. So yeah, you need to zoom in a whole lot here. Jack, I would recommend that you talk to your classmates, because I had them write a quadratic program freshman year, where you can solve any quadratic by just typing A, B, and C.
Yeah, quadratic.
And you should share that. So if you have a calculator that has a connection cable, you can share that with another person.
I don't have the cable.
I have the cable next door. So if you guys come by afterward, I can show it to you. But honestly, it would be easy. If you YouTube quadratic program, it will take you like 8 minutes to code it in your program. And you could just watch a video on how to do it.
Okay.
So if that's easier, you'll probably learn about how to do it also. But I would probably not go to graphing on this test because it's going to take more time to solve if the roots are this small. You know what I'm saying?
Yeah.
So have the program in your back pocket in case you need it.
Yeah, I'll look at that.
Type in quadratic program, TI-83, and you'll probably get 30 videos to show you how to program that in so that you can just type the A, B, and C value and it gives you the roots automatically. Okay? So what is 0.03526 times that number going to give us?
44,662.64.
That sounds good. 0.6. All right. So that's our final answer. That's what the scale is going to read when you jump on it from a height of 1 meter when it's fully compressed. What's going to happen after it gets fully compressed, though?
It's going to come back to...
Yeah, the scale will settle itself out, and it'll come back to 760 newtons, which is what it was to start the problem. Okay, good question. 88's a tough one. It's like a really short problem in the book, so it looks like it's an easy problem when you look at it first, right? But then when you realize the detail that goes into this problem, it's a rather lengthy problem. All right, next. It's open forum, so whoever says the next question gets it, so.
Number 3.
73 it is.
No, this is from...
All right, so let's see. We are now on page 167. This is number 73. It says the following. A 36 kilogram crate, look what I'm already doing, right, as I read the problem, starting from rest, is pulled across a floor with a constant horizontal force of 225 newtons. For the first 11 meters, the floor is frictionless. For the first 11 meters, the floor is frictionless. And for the next 10 meters, the coefficient of friction is 0.2. What is the final speed of the crate after it's being pulled? Okay, so the first 11 meters, it's frictionless. We have a force. We have no starting velocity. So we could figure out the velocity after those first 11 meters. That would be my starting point. I would look at this problem in two parts. Here's my object. Here's my force being applied to it. Here's my floor. This is a distance of 11 meters. And then we hit this surface that's got friction for 10 meters. Okay, here's the object at this moment. And then we'll look at the object again at this moment. So, I would truncate this problem into two parts when I'm looking at it. Now, do you have to necessarily? No, you actually don't. You could figure it out another way. But I would personally recommend doing this because I think it would be an easier approach to the solution. So here's what I would do. I would start this by looking at the fact that it's horizontal. It's horizontal. It's horizontal. What does that indicate to me when it's horizontal?
Theta is either 0 or 180.
Good. Theta is 0 or 180 to start. If I'm applying a force in the same direction of motion, then it's 0. If it's friction, it's always going to be 180. Second thing, because it's horizontal, what else? Is a huge part that we have to make sure we're making clear. Because it's horizontal, what can I use? What can I use when something is horizontal? That is very useful for sure, which we're going to see play a role. Absolutely. So he's already getting at the point that, you know what, Fn is acting up and Fg is acting down, so those are balanced because it's a horizontal force applied. Really good point there, Eduardo. I wasn't even thinking of that, but that is absolutely true. So we could already put a little side note that Fn is going to equal mg in this problem because it's horizontal motion. There's one other thing that's really important that we haven't said yet. I'm not going to use conservation of energy here. That's a hint. I'm not going to use conservation of energy. I could, if I want to. I could. You could always use conservation of energy. Any problem, you can use it. Any problem. But what can you use in this problem that might simplify things or make it a little easier for you to look at? Because it's only horizontal motion. If you're not using conservation of energy theorem, what theorem could you use instead?
Kinetic energy.
What is that called? It's not just called kinetic energy.
Half mv squared minus half mvo squared.
So what is that called? The work kinetic energy theorem. So write yourself a big note. When problems involve only horizontal motion, you can use the work kinetic energy theorem. Because the work kinetic energy theorem does not involve what? What does it not involve? Potential energy. So if you have a spring, or if you have vertical motion at all, you should definitely use conservation of energy. But because it's horizontal motion, you should use the work kinetic energy theorem. So we can start this problem by saying W equals delta KE. But the problem is this. We've got two parts to our problem. Let's put a dotted line here to show. This dotted line separates each part. Part 1 and part 2. We need to look at these parts independently. But here's something to recognize. The velocity that the block has after part 1 is equal to, I don't want a number, but tell me what it's equal to. Not a number. I want a concept here. God bless you. The velocity at the end of part 1 is equal to?
The initial velocity of the second part.
Say it louder.
The initial velocity of the second.
Of the second part. That's got to be something we get our minds wrapped around. So if you end the first part with a given velocity, it means you're starting that second part with that same velocity you ended the first part with. So we have no velocity in the very beginning. So right here in the very start, right, when the object is there, the velocity is 0. I wrote that down already. But then the velocity it has here, we're going to call that V2. And then in the next part, we're going to call this V3. So we really have from V1 to V2, and then from V2 to V3. So we're looking at this in a truncated fashion, in a piecewise fashion. So if I'm using the work kinetic energy theorem, my work done is force times distance times cosine of theta, and that equals my final kinetic energy minus my initial. Again, I'm only looking at part 1 right now. No friction involved, nice and easy. The initial kinetic energy is 0 because there's no velocity to start this problem, so that drops off. So we know that force times distance times the cosine of 0 degrees equals the final kinetic energy. Now, because I've been using 1 and 2, I'm probably going to do that here also, so maybe do this if it helps you. Okay, to keep our subscripts in line. The first part 1, the second moment 2, the third moment 3. And maybe if you want to not confuse 1 and 2, maybe call this A and B instead. If that helps, call that part A and call that part B. You see what I'm saying there? I don't want you to confuse part A or part 1 and 2 with, the velocity 1, V2, and V3. Because we really are looking at 3 moments in time. The beginning, the moment where it transitions from no friction to friction, and the moment at the very end when there's only friction at the very end of the problem. Now, why is it 0 degrees in this problem? Why did I plug in this 0 already? What's happening here? Someone besides Jack? Sebastian?
Because the force is acting on the object, pushing it to the positive value.
Yeah. The direction of motion is to the right. The applied force, Fx, is to the right. So the angle between two horizontal vectors to the right is 0 degrees. So cosine of 0 is 1, which makes life easy on us. It becomes this now. And what's our goal? What are we trying to figure out for the first part, or part A? What are we trying to figure out, Christina? The velocity right as it hits the transitional period, before it hits the friction. That instant before it hits the friction, we're trying to figure out what is this velocity right here. So we're trying to find out V2. What force is applied in this problem? What's the applied force equal to in this problem? 225, it's right here. Remember, there's no friction, so this is the overall force, 225. The distance is 11 meters. The mass is 36 kilograms. So please solve this for V2. All right, there's V2. What do we get as a number for V2? So this is not my final answer, but I'm going to circle it for now, so to remind myself that this is the velocity the moment it hits the frictional phase. We're then asked, what is the final speed of the crate after it's pulled the full 21 meters? So we're looking for really V3 now. We're looking for that velocity at the end of being pulled 21 meters. God bless you. Through parts A and B together. Now, how does part B change? There's a couple things we have to recognize. Give me one thing, Natalia.
You have the initial velocity.
You now have VI, or V2 in this case. But yes, initial velocity, you have velocity here, so this is not going to drop off in the work kinetic energy theorem now. Does everybody see that? Okay, what else? What's the other change?
The force is now friction acting with a 180-degree angle.
Yeah, so we've got the pull force still, so we're still going to use this, right? Because you're still pulling on it for another 10 meters. But now we're going to negate friction from that, because friction is causing it to lose energy, right? So the work done by friction is, remember, like negative work. So in this problem, we want to then go to part B. Let me see where I can fit this on the screen. Okay. We then want to go to part B. And again, let's keep this side note up here that Eduardo told us earlier, right? Fn equals mg. We're going to use that finally. And we want to look at part B and say to ourselves, okay, now we've got, again, work equals delta K. We know that the work acting is the work done by the pull minus the work done by friction. And that equals K3 minus K2. I'm calling it 3 and 2 to indicate the third moment and the second moment in my diagram over there. The third moment is at the very end. The second moment is at that transition between frictionless and friction-filled. And our goal here is to figure out V3. So the work done by the pull is still Fx times d, minus the work done by friction is friction force times d, and that equals 1/2 mv3 squared minus 1/2 mv2 squared. Now, the one thing that makes this a little bit tough is that FF has a formula, but we already said FF is mu Fn and Fn is mg. So if it helps on the next line to write this, this is going to become mu times mg. Still with the d there. And we know everything. What don't we know? V3. Mu is given in the problem, by the way. I'll write it down. Where is it? Mu is 0.2. And our new distance traveled for this problem is only, what, 10 meters in the second half? Yeah. So the d value for the second part of this problem is only 10 meters. Besides that, everything else is really the same as it was earlier. We've got, and we're solving for V3, so I would move this whole thing over, right? I would take this entire thing and add it over to the left-hand side and multiply by 2, then divide by m, then square root it, right? So move this whole thing over, or plug in at this point if you want. If you're comfortable plugging in, by all means, you can plug it in to solve algebraically. Solve for the algebra, the variable that's missing, which is V3 here. So I'm going to just write it out so you can all see it. Oh, you know what we can do also is we can start factoring stuff out, but that's just going to get a little messier for now, so I'm going to leave it alone. And then I'm going to solve this equation for V3. Okay, it's just going to be really messy is what's going to happen here. So it looks really complicated, and I get that because you've got a lot of variables here. But if you're careful and you're meticulous with your work, those variables become a little bit easier, actually. Just moving stuff around and solving algebraically in the bottom right there. But again, please, by all means, you could plug in at this moment right here and then just solve for V3. Did you get a number for V3?
Yeah.
Yes, nice. What do you got?
16.08.
Thank you, sir. I appreciate that before you left. See you tomorrow. So, V3, the answer is reasonable. How do I know that that answer is reasonable? What's the one thing that indicates that it is definitely a reasonable answer? Nobody? Think about it. Compare it to the last answer.
Since the initial velocity was higher in the second part, and you're doing all that math there, it should be higher.
If what? There's one if statement you got to add to that. This number should be higher if the applied force of 225 is still greater than friction.
Correct.
Hypothetically, if I'm pulling with 225, right, and friction is pulling back with, say, 500, then that's a negative net force, which would make me slow down, right? But because my 225 is more than friction, can we figure out the friction force? What's mu mg? 0.2 times 36 times 9.8. 0.2 times 36 times 9.8. It's going to be like 180. Probably like 170 something. 0.2 times 36 times 9.8.
70 point.
What is it?
70.56.
78.
70, just 70.
0.2. Duh, I did 0.5. So far less than 225, right? Far less than the value that we're pulling with. So we're pulling with 225. Friction's only pulling back with 78 newtons. So even though friction is still acting on it in the second part, my pull force or your pull force is greater than friction. So the net force is in the direction of the pull, which means that it's going to continue to speed up. So this answer should have gone up from here to there. So 11.73 becomes 16.083 instead. Yes?
I understand why, but it's a little, just because the second part there's friction,
Mhm.
just a bit strange for me that it goes faster.
Well, the thing is this. Even though there's friction involved, you're pulling still. If you weren't pulling, then it has to go down as velocity. So if you let go of it, right, and the problem tomorrow could be now you let go of the box. Could probably be this. Now you let go of the box, and it's sliding on its own. Then the answer will definitely be less than 11.73.
Okay.
Because then only friction will be acting on it, and friction does what? It decreases your energy. It lowers your kinetic energy, lowering your velocity. It's an opposing force. Give me 1 second, guys, just because Coach Rotman and I are figuring out practice, and I know he's waiting for me.
What time's practice?
We were going to do 2:30, which it is right now. That's the issue I'm running into. I know.
Oh, so
I'm just seeing what he says. Hold on. He won't be back until around 3, he said. Okay. Are you in a group chat with the whole team?
I'm not, but I can tell some.
Can you text somebody to get in on that?
We'll practice at 3, you said.
Do you think they'll cancel like MLB season?
Yeah, could you